just record from this point onward. Just a small oopsie. We'll start with the code. I think that's at least a reasonable starting point too.
Yeah.
So to make this more concrete, because the notes in the book are it's one thing to see the theory, but it's another thing to actually see the code and what's actually happening. So they started off with just a simple Python list just to show what's kind of happening. So they've got this list A, it's got 1, 2, and 1. You can make the list and then you can inspect the list. You can say, okay, grab the 0th element, which is 1. And then you can say change the second element to 3 and then print that off. And you'll see that now the list is 1, 2, 3. And they're showing that you can do something somewhat similar in Torch. So we're importing Torch. We're making an array of just ones. It's of size 3. And then we can look at it and we can see that the type is a tensor and we've got 3 ones like we asked for. And then same thing in terms of the indexing. If we want to grab the first element, then we're grabbing just the tensor that is right here, the 1. And then if we want to, we can break it out of the tensor and we can just cast it to be a float. And then now it's just 1 instead of being a tensor 1. And then we're showing the same process of just assigning to it. So we can plug in 2 in the second index, and then it becomes a 2, whereas before it was a 1. And so this section, they're assigning 6 zeros. So it's a tensor with size 6, and it's all zeros. And then they're going through and they're individually assigning all of the points. And so this is kind of annoying because you have to go in and you have to say, okay, 0 is this, and 1 is this. And instead, what you can do is you can just directly pass a list or a NumPy array, and then it will generate the same thing. And it's much less work than defining every individual point. You can just import it all at once. And same thing as before, you can just cast them to be floats, then it breaks it out of the tensor. One thing to note, we'll talk about it more when we get to the GPU section, but this doesn't entirely work once you push something to a GPU, because this is either pushing it to NumPy or it's pushing it to just standard Python stuff. And if you have something that's on GPU, you have to detach it and push it to the CPU explicitly. So just something to note if you ever run into an error like that.
Just a question on that, in terms of the detaching from CPU, and what's the flip side of it? Do we like push to, like, is there a command to push it to GPU? Like, I think there is something called toCUDA or something, right?
Mm-hmm. Yeah. So by default, it will be on the CPU. But then if they have it somewhere down below. So if you can directly define something and say, put this directly on the CUDA device. And when you do this, it'll just push it to all GPUs.
It puts, so if you have multiple GPUs, it puts them on the first one, or?
Yeah. You can say :1 for the second one, :2 for the third one.
I see. Okay.
Yeah.
Okay.
Yeah.
Okay.
By default, it'll go to whatever your default device, which is typically 0.
Okay.
But yeah, we can talk about that in a second.
Cool. Thanks.
So previously we were looking at these points. So looking at the shape, we can see that it's just a single length 6 axes. And then looking at this one, we're defining a new array. And you can see that now it's these nested lists. So it's 3 lists of 2. And that's how it becomes this new axes, or this new set of dimensions. And when we print that off, we can see now it's a 3 by 2. So it's 3 this way, 2 that way. Don't know why they're repeating this. This isn't that interesting. So with this, what they're doing is they're showing that you can define zeros, and previously we just told it 6, but in this, we're telling it, okay, make it 3 on this axis and 2 on this axis, and if we want, we can just continue to add more, and it'll just add more dimensions to it. So if you want to make any n-dimensional array, you can just directly define all the dimensions and it will sort that out for you. And so when you have these multi-dimensional arrays, you can index them in various different ways. So you can say, I want this point from this row and this column, or you can say, I just want the this specific row or this specific column, or there's tons of different ways that you can cut that. Just depends on what exactly you're trying to select out of that. And I think after that, we'll go back to the notes because this is when it starts getting into the storage stuff. Any questions related to the code at this point? No? All right. So they had a section on the name tensors. They mentioned that it's experimental though, and I've never personally used it, so I can't speak to it a whole lot. My understanding is you can basically assign a name to all of the different axes, and then if you try to do certain operations, it will align them for you. So if you have something that is, let's say you have an image, and some images are sorted. So the first axis is your red, green, blue. Your next axis is your width, and the next axis is your height. It might be possible that you have another image that's width, height, and then RGB. And if you want to do some operation, like you just want to add 2 images together, the name tensors would be able to just unravel that immediately. So you don't have to do some transpose operation. It will just figure out, oh, these are the ones that go together. That's at least my understanding of named tensors. I've never used them though, and it seems like they're kind of still an experimental feature. So I wouldn't worry too much about those.
Ryan, can I make a comment about that?
Yeah.
So I haven't used them, but I am actually looking forward to named dimensions, because just one slight difference. What I remember reading is that PyTorch will not by default align the dimensions. There's a function you can call that says, hey, just align these, but by default it won't. So assuming that you use your identical code that you have right now with unnamed, if you simply name them, all that's going to happen is it's going to do an extra check to make sure that anytime you try and add similar things or multiply things, whatever, that the dimensions have the same name. And it'll throw an exception if for some reason you have them misaligned.
Mm-hmm.
But otherwise, you don't explicitly have to do anything other than just provide the name when you're creating something. And so that's how I see using it, is not to like have it figure out the math for me. But a lot of times I'm looking at code and I'm like, oh my God, so it's batch and then this and then that. And then it's like 4, 5, 6 dimensions, and trying to keep track of them, it kind of makes my head hurt.
Mm-hmm.
So even if you did things exactly the same way you're doing now, if just upon instantiation at some point you said, by the way, it's channel, then height, and then width, then later on, anytime you do anything, if you get height and width swapped, then it'll yell at you.
Yeah, that's a good point. So the next section, talking about the element type. So we already talked about this a little bit, actually. So when we have lists, it's really inefficient because they can be any number of different things, and we can't do various different optimized operations. And if we have C code, then we can do a lot of things much faster than we could with Python code. So these are all the same data type, and on top of that, we need to understand what the different data types are. In the book, they showed that you have floats of varying different precisions, and then we have integers of varying different precisions, and then we have booleans. And there's another thing to note is there's also CUDA data types. So if you're pushing something to a GPU, sometimes you might also have to say CUDA something, blah, 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 blah. But it's typically the same. It would just be like CUDA dot float32 or something like that. It's not any major overhead. And I believe that when you push to GPU, it will automatically cast it to the correct comparable type. But I'd have to double check on that. If you want to check on the data type, you just have your tensor and then you just say .d type, and then it will tell you this is a float32, this is a float16, this is whatever. So that's the gist of that. One thing that is important and kind of a recent development that wasn't mentioned in the book is a lot of things are starting to use mixed and half precision. So there's this NVIDIA Apex package. And what this does is it's an extension on top of PyTorch that allows you to train neural networks and do various different things in half precision. And this can be good because it can make the memory footprint much smaller, but it also can be helpful in terms of speeding up some of your calculations if you have the right kind of processor or GPU. So the newest series with tensor cores gets a decent speed boost from the lower precision because that's what they were specifically designed to do. And I've used this quite a bit because in the past when we were working with the big natural language processing models like BERT and all of the other stuff that's popular, being able to do large batches and keep a lot of stuff in memory all at once is pretty important. And if you can just say, instead of doing float32s, let's do float16s, and we can do double the batch size, that's actually really useful. So I've gotten good use out of that. And another thing is the more recent builds of PyTorch have started using automatic, they have automatic mixed precision built in, which is really nice because the few times I tried to install Apex, it was just a complete pain in the neck. So it's nice that it's finally built directly into PyTorch, and we can use this directly instead of needing to install some additional plugin. I know that at this point, there's still some difference between the two. I don't know exactly what it is, but that's a feature that you should probably know about if you're ever trying to apply to really big neural networks or even if you just want some speed gain. People have done various studies and they've found that there's really no big decline in performance just by using the reduced precision. The next section.
So,
yeah, go ahead.
On the question, like I had a question on the FP16. How do we do it? Is is there a specific command we give to a tensor, like you said, .2 FP16 or something like that to make it mixed precision?
So there's good documentation for it. It really is just a difference of a few lines of code.
Okay.
So I think they're showing it here where basically you just say, wrap this around your various operations and it will automatically scale it. And then let me look if I can find a better example. But it's not very much work. When I've worked with it in the past, it's just a few alterations.
Sure. Now, I was just wondering if it's as simple as doing like casting. Like, can we do like type float16? Is that even a thing?
So there's a bit of trickery that has to go on. So it's not quite as simple as just casting it to the type, because there's various different operations that don't play well with the lower precision. Yeah. So the way they've configured it, it kind of intelligently decides, okay, we don't want to do this during the batch normalization step, and we do want to do it during this other step.
Okay.
And so the reason it's mixed precision is it's intelligently saying, okay, we want to cast it here, we don't want to cast it here, we want
Okay.
it to be this type, and so on.
Cool.
Yeah.
Hey Ryan, I was going to ask, are you comfortable sort of defining mixed precision in terms of like why it's not just all using half precision, why it's actually mixed?
Um, I haven't particularly studied it, but my understanding is there's just certain pieces that are more fragile to the reduced precision. Um, I'd have to look at it more. I don't really have a great
Okay.
explanation of that. I just know that there's certain pieces that are fragile, and if you reduce the precision, it can cause instability and stuff.
Yeah. So I don't know if somebody else can help with that. My understanding is, say for example, you have your weights. You might need to store your weights in a full float 32, but you can do the batch in float 16s, and then you just add whatever difference to that float 32. But you wouldn't necessarily want to degrade, for example, your weights by only storing them as float 16s or something like that. So that's why the term mixed. That's why it's not just, hey, just speed everything up by doing everything in float 16. So there's a few places, like Ryan's saying, where you really want to be able to have small increments. And so you need that extra precision.
I know there's when I've used AMP and Apex in the past, I've seen that there's something tricky in the background going on where it's saying like, oh, we got an overflow on this, so we're changing some factor to a different multiplier or something like that. I haven't looked at the details of exactly what's happening there. I've kind of just used it as a black box for some free optimization.
Yeah, I mean, just thinking out loud, I was wondering which cases would we need such high precision, like in terms of float 32. I guess, I mean, where would that actually make a difference? One thing that I could think of is like maybe when it's like super low learning rate that you're multiplying your weights by, you definitely want to be very sensitive to not overshoot that, and by approximating, I would think is one example.
Mm-hmm. Yeah. I saw there was a question about the graphics cards, and I think Ted, you already answered it, but just to share with everyone else, you can do mixed precision with pretty much any NVIDIA card, but the newer ones with the ray tracing and the tensor cores are the ones that you'll see an actual like speed benefit. If you do it on an older card that doesn't have the tensor cores, it will just be a memory saving. It won't necessarily be a speed up. So that's something to keep in mind. You still can do it. It was important for me in a previous competition. I don't have a GPU with tensor cores, but it was important because without it, I couldn't even fit a batch properly because it was too much memory. But with that trick, I was able to fit batches in there. So 3.6, looking at the Tensor API, I left this one kind of empty because all the chapter is really saying is, if you look in the documentation, there's a whole bunch of different operations you can do on these tensors. For us, the important ones are typically the matrix multiplication and defining noise and various other things like that. But there's a whole pile of things in there that you can look around, and I'm sure they have applications in different domains and stuff, but the majority of them are kind of just your core neural network focused operations, like the matrix multiply. Then looking at 3.7, tensors, scenic view of storage. This was showing that the way these are stored, it's a contiguous memory. So if you look at it, if you look at the actual storage, it's just like a massive list. It looks like it's all one big long array. And then in order to get what we actually display when we print it out, we've got a stride and a size and an offset. And that's basically saying, okay, take that big long array and format it in such a way that it's a 3 by 3 by 2 or something like that. And then one thing to keep in mind is, since a lot of what we're seeing is just a view of the variables, we have to make sure that we're not doing some operation that's overriding something else that we're using elsewhere. Because we might do something and we're operating on a view, and then we make some change and it changes the underlying storage. And then we have some other variable that we wanted to stay the same, but now it's altered because the underlying storage is there. And anyone who's used NumPy a bunch has probably seen the same happening, where you might have some kind of unintended movement of your variables as you're doing some changes on them. Any questions on that, the whole storage and view thing?
Yeah, like when does the stride become useful for us to know about? Because I mean, from what I think, if stride is basically saying how far it has to jump, I think in the memory locations for it to get to places. So I think it would affect speed maybe, but like I would think such things are kind of handled in the background and something for us to know about while coding.
I've never really used I've never inspected the storage before when I'm doing things. So I think they're just kind of showing you, here's what's under the hood. I wouldn't really, I've never inspected the stride and said, oh, it's a three in one. So I wouldn't worry about it too much. I don't see a direct usage of it. They're just kind of showing, here's how it's organized in the back.
Sure. Yeah, I mean, as a practitioner, I'm always thinking of things that will definitely help me get more accuracy or speed. So if I do need to dive in, I'm happy to, but sometimes it can get a little too detail oriented.
Yeah.
Yeah, I think one thing that can happen is if you start with a bigger tensor and you grab a subset of it, then they use they talk about this property contiguousness. So that means that your n dimension has stride 1 basically. Maybe that's not the only requirement, but that's one of the requirements, right? So so if you pull out a subset, then you may want to know if it's not contiguous, because then you may have a performance penalty. And so depending on if you're doing like a heap load of calculations, it may benefit you to actually do a deep copy into actual contiguous memory and do the bazillion calculations that are faster, even if it requires a copy in and a copy out on the way back, right? But now you're talking, I mean, that's really esoteric stuff. Right?
Yeah.
Normally training a model, you're never gonna think about that.
Yeah. I guess more in when you're developing a library or something, I guess is when you would get into these things.
Yeah. So Tommy had a question in the Slack about that code that was doing the unsqueeze. And I played around looking at that, and then I noticed that, here, let me show you. I'm gonna share my screen, Ryan, okay?
Sure.
So this, at one point they compare IDs on two tensor storages in order to show you, like, see, this is actually pointing to the same thing. And I found that this ID on PyTorch storage is like completely bizarre. It's not, it doesn't act normally. So you can see I have this code here where I create a 3 by 3 tensor full of ones and a 2 by 2 tensor full of zeros. So there's no possible way that these two things could share storage, right? And yet, when I print the IDs for these two storages, they're identical. And I encountered the opposite when I was playing around with this unsqueezed weights thing or whatever. I was getting different IDs back, for their storages, even though they were actually the same. And so, let's see here. I don't know if I have it convenient. It's kind of a mess in the middle here, but basically you can see I've got like foo storage ends in 384 and bar storage ends in 000. But then at some point down below, what I did is I actually modified one of the values, and then both foo and bar got the modified value. So clearly they had to have been pointed to the same underlying storage.
Mm.
So anyway, I don't know a lot about how IDs work in Python, but I don't know if anybody else knows, but it did seem like there's some extra level of indirection that PyTorch is hiding from core Python, and IDs are not what you think they are.
So question there on the on your on the second example, you had like A and a B, I think, or a foo and a bar. Yeah. So how did you define this? Because isn't it dangerous that they're both like getting changed when you change one of them? Are they
Well, so
copies of each other, or sorry?
yeah, so this was from Tommy had asked a question in the Slack because there's this code in one of the examples where they call unsqueeze and then they call unsqueeze underscore.
Right.
And so it's like, oh, do they really need that underscore on the second one? And so foo uses the underscore and then bar
Does not. Yeah.
does not. And both of these are just views into the original weights storage. Okay. So neither of these is actually a deep copy where they've copied the numbers into a new chunk of memory. Okay. And so how I was able to prove that they're just, you know, views into the same chunk of memory is when I changed one of the numbers, you know. But so then I thought, oh, okay, sometimes you really want to know, do I have a separate chunk of memory? Because like, let's say I didn't want to change all of them when I changed the value of one, right? I want them to be separate. I'd want to know. And so I don't know enough about PyTorch, but you know, you could just use this code that they had in the book, which is, are the IDs equal? And then you know, if I change one, I'm going to change the other. Well, but it turns out that basically if you compare IDs, like you always get true. Okay. Even when these IDs are clearly different, it's like, okay. I don't know what's going on.
All right. Okay.
So at the moment, maybe later on the book, we'll see more stuff because I'm sure they're going to sprinkle things in even when the topic is something else like gradient descent or whatever, right? But at the moment, I don't know how to tell if I have two tensors, whether or not they actually overlap and share storage or whether they're physically separate chunks of memory and that if I modify one, the other won't be modified.
Okay. Question on your first example then with the X and the Y. Here, like you said that, okay. For now, let's not really focus on the IDs, I guess, because they're not reliable. So X.storage is giving you a bunch of ones with 9, which makes sense. So Y.storage, do you have that too?
Oh, yeah,
a Y.storage.
Yeah. Sorry, let me just scroll down a little. Yeah.
Okay. So, yeah, because I mean, like first look, you would think that somehow they got messed up, but they did not. So that's good. Yeah. Based on the IDs. Okay, cool. Thanks.
Mm-hmm.
Okay, I made a search in the book for the word mutable. It is never mentioned. So maybe we do not have usual Python mutability with tensors.
I don't know. I mean, clearly you're allowed to change values within a tensor.
No, I mean in Python, when you make two objects equal, then it is pretty much the one object with two names, different names. So if you want actually to create a new object which is the same, you are supposed to use another method which is a copy because of it. And it looks like in TensorFlow, a new element is created each time. That there is no, well, at least with PyTorch, there is no mutable elements at all. And each time when you write equal, a new object is created. Just, well, it is just the same as previous one.
Yeah, I mean, if I just have some code here and I say z equals x, okay, then I'm almost positive that this is not going to create a truly new set of memory. Okay, so z is going to be all ones, right? But if I say z and pick some random part of it,
You should have, you have two
oh, sorry,
dimensions. Yeah.
sorry, I forgot how I defined it. All right, so now z clearly is modified. It's got that 3 in there. And then if I go back in here and I say, what does x look like? You can see. So
It
z
is
was
changed, yes, it is mutated.
z was clearly just a view into x. It didn't allocate new memory for z. And a lot of times you're going to want this. So
Okay.
like, you know, I was doing
Yes, I
something and
understand.
I was modifying images. And so I want to be able to take one image out of a batch. I want to be able to overwrite a few, you know, of the bytes, and I don't want it to actually make me a new copy. So a lot of times that is what I want, and it's going to be super fast. But
This is
and
true.
clearly I could say like I want a deep copy of X, but I think there are some times when you might, I don't know, it just might be unclear, and so I don't know how right now to test whether or not Z and X share storage or not.
Well, this is very useful knowledge, which was not mentioned about are they mutable or not.
Yeah, I like the book so far, so I think that it may get covered. It's just right now it's not clear to me.
Hey Ted,
Yeah.
can you show us the second example again, where you compared the foo and bar? So in the cell 31, shouldn't you be comparing foo and bar?
Oh, I modified things. I played around with this multiple times. Yeah. So I don't even understand what's happening because these numbers are clearly different, and yet equal is returning true. So I started going crazy here, and then I was like, okay, let me just try something like something that's not PyTorch, right? And then say, so this will come up false. So you know, and generally in Python, I think this works, but I'm saying I think PyTorch, there's some level of indirection here where the storages might not truly be directly accessible. There still may be, like they mentioned, the whole Python buffer thing, whatever, you know. So I don't know what's going on yet. But by the end of the book, I promise we'll know. If it's not covered in the book, I'll research it. And so a few weeks from now, we'll have the answer. Yeah. But so just playing around right now, the only way I know is I just modify something and then I can prove whether or not they share memory. Because if I modify one, then I can just see if the other one changed or not.
Yeah, that's bizarre. I've always been a bit confused by how all of those things layer together. I pretty frequently will just kind of lazily, if something's not doing what I want, then I just say, okay, I'm going to do copy.deep copy to whatever object and then just make it go away, which is not probably always the ideal solution, but it typically is a reasonable band-aid. So back to the outline in the code. I could show some of the stuff with the storage, but I think you just kind of showed all of those steps, Ted. So just pointing that the storage is the same once you do a copy of it, basically. And then the next section, what they're talking about is moving tensors to GPU. So we talked about this a little bit. You have two different options. You can directly place it on the GPU when you define the tensor, or you can move something to the GPU with the to command. And what that looks like in terms of code is, let me find it. Something like this. So when they're defining the tensor directly, they're saying, okay, these are the values I want, and I want it to be placed onto the CUDA device. This will directly sit on the GPU by default. Alternately, you can already have a torch tensor, and you can push it to the CUDA device. And like was mentioned before, you can push it to a specific CUDA device or a specific CPU or a specific whatever. There's other devices out there too, but typically it'll just be CPU and CUDA for most people.
Hey, by the way, Ryan, total tangent here, but did you see that like there's not one pre-compiled for download, but that you can actually compile the whatever GPU compatible thing for your Mac, your Radeon GPU or whatever.
Yeah.
So then you wouldn't get that error message. I mean, you would never want to try and train like a full-sized, CNN, but it would actually allow you to run those basic operations without an error.
The GPU that the Macs come with is actually reasonably good. It's got like 4 gigs of memory or something like that. So you could theoretically, and from what I've heard, the AMD cards actually have quite a lot of compute capacity. They just don't have all of the driver support and that stuff. The big stumbling block, though, is you have to build it from source, which is just a bit annoying. So maybe I'll try it someday, but not right now. I think it might also be a second hurdle that it's being done on a Mac. I'm not sure if there's any additional difficulty doing that versus Ubuntu or something like that.
Mm-hmm. Yeah.
So that's how we move stuff to GPU, and then they talk about the NumPy.
Quick question on the GPU stuff. Are multiple copies placed on all of the GPUs if you have multiple GPUs, or is it just going to be on one?
It will be whatever you define it as. So like in this scenario, device CUDA, if you have 4 different devices, it will just place it on whatever the default is, whatever has the ID 0, most likely. And then if you want it to be put on multiple, you can say, okay, push it to all of these different devices.
Okay.
I haven't done a ton of stuff with multi-GPU. In my system, I have 2 different 1080 Ti's. And I've done some multi-GPU stuff, but a lot of the sort of frameworks that are built on top of PyTorch will just automatically handle it for you. And typically the way it's done is you have the full neural network will be on both GPUs at once, and then you'll just have the different batches of data going into both GPUs at the same time. So that's the actual implementation I've typically seen. I think it would be a little bit bizarre to have totally different data on each different GPU. So there is some copy. So you might have the neural network on both, but you typically wouldn't have more than that. You wouldn't rest a whole bunch of data on both at the same time.
What so if you have multiple GPUs for name assignments, is that done at the OS level, or is there some way that Python is assigning it, like this GPU is CUDA :0 and this one's CUDA :1, or I was trying to find a way to try to list that out, but I wasn't sure if anyone had any info.
I don't know the command off the top of my head, but there's a Python command to just basically say, list off all of the GPUs that are available, and then you can look at it and it'll say CUDA 0, CUDA 1, CUDA whatever. But that doesn't necessarily tell you directly, this is your 1080 Ti, and this is your 1070, and this is whatever other card is installed. And the way that I typically inspect that is I'll go into the terminal and I type in NVIDIA-SMI, and that will print out and it will just say, okay, this is 0, this is 1, and then it will show you all of the specs. And it shows this one has 12 gigs of memory available and it's 1080 Ti and the fan is running at this speed and all of that stuff. So I typically look at NVIDIA-SMI to do that. I'm sure there's some other automated way to get more information out of it in Python, but that's typically what I do.
I've seen snippets in PyTorch code. There is a thing that'll list your devices, but I don't know it off the top of my head either.
Yeah, I Stack Overflow it every single time I do anything with that stuff. I've been doing stuff with reinforcement learning, and I tried setting up two to run in parallel, basically because you have to run a whole bunch of simulations of your games. And so I used NVIDIA SMI to look at it, and I said, oh, by default, for whatever reason, this is only using GPU 0, it's not using GPU 1. And then I had to figure out what's the command to make it so this notebook only sees this GPU and this notebook only sees this GPU. And it's fairly simple to just find it on Stack Overflow, and it's like 2 lines of code just to say, change the environment a little bit.
For Keras and TensorFlow, I have this one cell in my notebooks that lists the devices and optionally disables devices. And so if I for some reason want to run something CPU, don't want to use my GPU, or if I'm using GPU in another notebook and TensorFlow is not very good about sharing GPU between 2 different notebooks. So then I just have this one cell that I copy to every notebook, because otherwise, yes, I would have to Google it on Stack Overflow. How do you list the devices?
Mm-hmm. So this is the kind of snippets that I typically use. It's basically saying, I don't know exactly why this is necessary, but you have to define it based off of the PCI slot. And then you tell it which ones you want visible. And so you'd think that typically what you do is you say, okay, here are the ones I want access to, but this works a little bit the opposite, where what you're doing is you're saying, I only want you to see this one specifically. And so that's how I run it typically, is you say, basically hide the GPUs from this notebook and then hide the other GPU from the other notebook. And then you can run the 2 in parallel, and the other one doesn't even know the other GPU exists. So it doesn't try to access its memory or steal space or anything. And I believe that this line is the one that will actually tell you about the different devices, but I'd have to run it and see on a system that actually has GPUs.
Yeah, that looks right. And it also lists your CPU too, not just the GPU.
Yeah. So moving on from the GPU stuff, they talked a little bit about the NumPy interoperability. We talked about this a little bit. You can load in data from NumPy arrays, or you can take stuff from Tensors to NumPy arrays, and you can do various different things. And that's nice because there's some times where there might be some SciPy thing or any number of different things that you might need some operation that's not natively in Tensor format. And so you might have to convert it to a NumPy, do some operation, then put it back as a Tensor. So you might do that sometimes, or you might just have something that you don't need it on GPU anymore. You can plug it in as a NumPy array, and then you can save room on your GPU if you want. The next section, they were talking about generalized tensors, and this was kind of a vague chapter. They were just basically saying there exist other backends, but you'll probably always interact with the Tensor API in the same way. So they mentioned I forgot what it even was, quantized tensors that might be doing something different in the back in terms of storage or implementation or something of those lines, but you'd still probably still call shape and size. And if you want to do the transpose, you do some certain line of code. So they're just letting us know that we'll be looking at that later. They mentioned chapter 15. And then the last section, they're talking about serializing the tensors. So if we want to write something to disk, if you do some computation and then you want to save it, or you train a neural network and you want to save it for later, this is important because you have to write it to disk. Otherwise, when you turn your computer off, you're going to just lose it, or you close your notebook, or whatever other scenario. And so there's two different options here. One of them is you can do torch.save, and that will basically just like wrap up whatever was happening in your variable in a pickle, I believe. And the issue with that is you can have compatibility issues in terms of if you change your PyTorch version, sometimes that causes problems. Or if you are trying to go somewhere else and actually reuse the file and they don't have PyTorch installed at all, then you can't load it at all. And so a more agnostic approach is to use HDF5. I'm a big fan of this format. There's a lot of flexible things you can do with this using the H5 library. And what that does is it stores it in this really nice, accessible array. And you have lots of different dials that you can fiddle with. So you can just directly say, I want to store this matrix. I want to store this array of weights. And you can name the different data sets. So you could make one file and you could say, this is my weights, this is my data, this is my optimizer, this is my whatever else, and you can just name all of those and it will all sit in one file that you can then load later. And then when you want to access them, you just access it sort of like a dictionary and you just say, okay, now I want to grab weights, now I want to grab whatever else. And then on top of that, it has various different options in terms of compression. So you can do gzip and all of those other variants, and you can save some space through that. And then the other nice feature within HDF5 is you can do tiling and various other tricks that allow you to optimize. So if you have images, it doesn't make sense for you to constantly be loading in the entire array or disorganized pieces of the array. You just want to load one image every time. So you can tell HDF5, organize the data in such a way that I can quickly access a 512 by 512 by 3 image, and it will be efficient at pulling out one every single time. And so I'm a big fan of that format. I've used it in a lot of different projects. So I recommend going in that direction if you can.
So Ryan, with the HDF5, we can save, like you said, we can save optimizers. I didn't quite understand. Like, are the optimizers also represented as arrays?
You can kind of save arbitrary things. I think optimizers was probably a bad example. Typically, it would just be data and matrices.
Okay.
But I have seen people take full dumps of like the whole environment. So if you try to continue training again.
Right. Because I mean, I typically use FastAI, which is built on top of PyTorch, and we save learners, which are basically like that whole thing, like optimizer, your learning rate and everything. And then you just learn.load and you just resume training, so to speak. I'm not yet familiar with something like that in PyTorch, if there is like a thing like that. But for that, I was having a hard time conceptualizing that as an array because there's like so many things going on in that.
Yeah.
Another question I had was for HDF5. Is it also compatible with TensorFlow or Keras?
Yeah. So it's very you can load it in as just a NumPy array, and then from there you can go to whatever else you want. And there's actually tools within TensorFlow to directly load data from HDF5. HDF5 in TensorFlow, they always use TF records, but it's very, very close to HDF5, so it can be plugged in fairly interchangeably.
Thanks.
Yeah. Any other questions? I think that's all the way to the end of that chapter.
What
So just-
Keras uses for serialization of its model?
Can you repeat that? I didn't catch the first part.
Well, when you do model in Keras, you cannot use pickle to save it, it doesn't work. You need to use its own Keras method. What is used over there?
I believe that it is using HDF5 in the background. I'm not entirely sure. I have to look. I'm not confident.
I was curious about the use for HDF5 as, I guess, opposed to grabbing data from like a SQL database. I mean, normally, is it faster than that? I guess if you just store it locally, like if you do your manipulations and then just store it in an HDF5 file and load that for later use. I'm just curious on people's experiences and what their thoughts were, as opposed to like querying SQL or, you know, grabbing the CSV file data again or saving in that format.
So I don't have as much background with the various different databases, so I can't directly talk to their speed. But in my experience, it's been the fastest to interact with it in HDF5 or TF records. I'll take a second and see if I can find the thing I looked at a while ago.
While Ryan's looking, I'll just mention I saw this cool comment somewhere else that if you're using compression that within the HDF5 protocol or whatever, it can use the kind of compression that allows indexing. So if you have tabular data, not only can it compress it, but it can compress it such that you can say, I want row 1235, and it can still go in there without having to read the first 1234 rows in order to decrypt it, decompress it. And so I thought, wow, that's really cool.
Mm-hmm. So this is this site that I looked at a while ago, and they show a few different methods. So let's say you have some images, you have lots of different options, but one of the simplest is, let's say you just have a whole bunch of JPEGs or PNGs or something like that. You can just leave them like that. But one of the issues is you're doing a whole ton of seeking if you just have a million images all in one folder potentially. But then on top of that, you're also doing some either compression or conversion to NumPy arrays. And so that's going to take a little bit of processing power and slow you down a little bit, rather than just having it natively what you want. And so they benchmarked a few different methods. So this Lightning database, I don't have very much knowledge of, but my understanding is it's basically just putting in everything in memory, and operates a little bit similarly to like SQL, where you could just extract that stuff out. I believe they have, yeah. And so they show various different benchmarks for things. So they show that LMDB on this small example is fastest because everything's already in memory, and HDF5 is actually the slowest. But then when they grow this to many, it turns out that HDF5, as you add more and more images, turns out to be the fastest in terms of storing images, and then also in terms of reading images when you start getting too many. So you can see just going from PNGs takes a long time. LMDB is pretty fast. HDF5 is even faster than that. So I've used HDF5 quite a bit, and I found it pretty useful. I can't guarantee if it's the fastest method, but I've gotten good use out of it, and I've talked with other people, and they've used it as well.
So Ryan, the idea is that you would open a large HDF5 file and keep that pointer open, and then you can read multiple images. Say I want the first image, the second image, the 100th image, whatever, versus if you were just loading individual JPEG files, each time you would be going to the disk and say, open me a new file and read it in and decompress it and all that. And that's why that one was like linear. Like,
yeah.
Well, and I think the book mentioned that it has a key value paired to it. So is that how you reference if you're trying to look specifically at a certain image?
So you can, I've organized it a few different ways in the past. One of them is that you can, so there's this concept of data sets. And so within a data set, you could have your data set be not the URL, the path to the image. So you could say this is image 2571.jpg, and that's your data set. And then when you call to that specific data set, it will load in that specific file. But then alternately, what you can do sometimes is you can make it one massive contiguous array, and you can say, this data set is my images, and it's a whole bunch of stacked images, basically. So you know that you want to grab the 2571 index out of your images data set. And there's various different advantages to both. If you do it as one massive contiguous thing, you get better results in terms of compression and random access potentially. But if you do it with the each one is its own data set, it's a bit nicer in terms of you don't have to keep track of what index is what image and so forth.
Cool, thank you. Could you link that in the chat, that article?
Yeah. And I see that this is saying that Keras uses HDF5 to save and restore models. That answers that question too.
Oh, thank you.
I put it in the book club Slack. I try to put stuff there because if not, then it disappears at the end of the call. Any other questions or anything for us to discuss? Maybe we can go to some breakout sessions.
yeah. By the way, just a real quick Zoom question, since you mentioned that. I've seen in the Zoom settings, there's a way to save the chat to a file. But what I don't know is after the meeting's over, if I'm the host, am I able to do that? So I don't know if any of you guys are Zoom
So
experts.
I think if you record it, at least I've seen in other groups, when you record it, it also saves a record of chat too. So,
Okay.
so wherever your admin location is, it should have that. Yep.
Thank you. All right. So we have a little bit of time. Do you guys want to do breakouts like we did last week?
Sounds good to me.
All right. So let me try.
Breakout, or is there a topic like discuss the book or say hi again, or?
I think free form. So so there are a couple names I don't recognize. So there are some new people. So you can say hi, what area, what industry you're in, like that. But then also, yeah, if you guys want to talk about the book, by all means. So All right, let me try this. Let me see if 4 is a good number of rooms. And then I will send out a broadcast message when we're getting close to the end of time. And then when I click the button, you don't have to stop talking instantly. It's going to give you 60 seconds to wrap up. You don't have to leave the instant you see the closing message. All right, here we go. All right, there.
To just
I
hello.
we get anyone
Hello.